welcome back to this Battery 2030 webinar. In this afternoon, we will get Idoia Barrio, if I'm not wrong in reading it, sorry, yes. And Idoia Undarpilleta, both from CDEC. Idoia will be the speaker, and she will explain us everything about lithium-ion production. Idoia Undarpilleta is the head of Energy Materials Unit and technical manager of Battery Pilot Plant in CDEC Energy Storage. We already learned something about CDEC this morning from Irace de Measa, who gave us this lecture on different cell format and how and the stories around the production of lithium-ion cells. This afternoon, you see that we already shared this screen in which you have more or less roughly how this afternoon session will be organized. It's the first live session we are doing, so it's also an experiment for all of us. Let's hope that everything will work properly. But it's the way we can get in order to show you really step by step how cells are produced. The idea is that the first step will be mixing, coating, and calendaring of electrodes. So Idoia will explain you everything about it, also secrets and tricks. And finally, you will get 10 minutes of question and answers. So please use the question and answer box for that. And Aitor will select the most important ones or all of them if possible, if there will be time enough. Second section will be on cutting and stacking, then again a question and answer section, electrolyte filling and forming, and again a question and answer section, and finally cell characterization and testing. And so we will end the day. So thank you very much, Idoia and Aitor, to help us in this. We are very proud to have you here. And so I think we can start. The floor is yours.
Okay, so good afternoon to everybody. And thank you, Silvia, for the introduction. And thank you for giving us the opportunity to show what we do here in CDEC. As Silvia mentioned, we are going to show you all the battery production, starting from the mixing. We'll explain the coating, the calendaring, the stacking, how we fill the electrolyte, and at the end, we'll say some words about the characterization of the cells. So let me start saying a few words about the CDEC energy storage. We are a technological center covering the gap between the basic industry, the basic research and the industry. There is very good people at the universities getting a very good results, but sometimes, or in general, I would say it is difficult to translate these results directly to the industry. So CDEC just is there just to bridge this gap. And the battery manufacturing pilot plant is playing a big role on this transfer of the knowledge from the basic to the industry. Once I have said that, and before going directly to the pilot plant, I would like to highlight the work that is done in the lab before we go to the pilot plant. Okay, in the pilot plant, everything is big. You know, we are working with big quantities of materials and so on. So any change you wanna do is gonna be very costly. It's gonna be very costly in terms of time and money. So before we go to the pilot plant, it is very important to have the ideas clear. So for that, we do a lot of work in the lab. We prepare slurries, 50 grams slurries in general, just to do the optimization of the formulation. We do a benchmarking of materials, formulations, whatever. We have a small doctor blade where we do the coating and we do the testing at the coin cell level. We also have a small calendar in the lab, and we play with the densification of these electrodes before we go to the pilot plant. So as I just said, very important to have the ideas clear. What we want to produce in the pilot plant. The specifications of the electrode, they have to be very clear before we go to the pilot plant. For sure, the transference from the lab to the pilot plant is not direct. We need to do an upscaling process, but we have clear what we want to produce. Okay, so once I have set this, we'll go to the first block where we will explain the mixing, the coating, and the calendaring of the electrodes. Yeah, okay, so let's go to the coating lab. Okay, so in the first step in the battery manufacturing plant is the slurry preparation. We have two different planetary mixers. The one that you are seeing in the image is a 5-liter planetary mixer. We have another one of a 15-liter capacity that is located in another room. The two planetary mixers are are separated because we want to avoid the cross-contamination. Now, at this moment, you are seeing my colleague Iker adding the CMC dispersion to the powder, to the solid powder. So in this point, it's very, very important to optimize the mixing procedure. So the mixing procedure and the dispersing sequence, they have to be adapted depending on the electrode that you want to produce and the electrode you want to design, okay? So typical anode formulation, it is composed by graphite, active material, graphite, 90% in weight approximately, conductive material, carbon, 5% in weight, binder, SBR, and we use CMC as a dispersant, 2% in water. In general, we try to process the anode in water. Not all the active materials, in general, they are very hydrophobic, and it is very difficult to process them. But having these mixers, these planetary mixers, they will allow us to prepare the slurries in water. Sometimes, you know, when you are optimizing the mixing procedure, you need to include a step where you are using high shear. So this provokes some bubbles in the slurry. So with this type of mixer, we have the possibility to make some vacuum and to get rid of all the vacuum, all the bubbles that we have generated in the slurry. So, okay, now Iker will go to the other planetary mixer that I mentioned before. We have prepared a slurry due to see how it looks like. So he will open the mixer, and this is a cathodic slurry. Okay, the typical formulation for the cathode, it is composed by the active material that it can be LFP, NMC 111, 532, 811, 95% in weight approximately, conductive material, carbon 5%, and binder PVDF. In general, we process these materials in water, but it is much more difficult to process them in water than the graphite. Okay, so now let's go to the coating. So once we have prepared the slurries, okay, we have to coat them on copper, or we will coat them on aluminum. The typical thickness of copper we are using is 8 micron, and for the aluminum we are using 15 or 20 micron substrate. Depending on the type of electrode we want to produce, we will use two different coating heads. We will use the knife system, or we will use the slot die system. Now you will see it in the image. Okay, so the slot die system is a post-metered system, pre-metered system, sorry. That means that the amount that we are putting on the current collector, it is controlled by a pump. So that means that the precision of our coating will be much higher. When we are using the knife as a coating head, the thickness of the electrode will be controlled by the gap between the knife and the roll, okay? So once we do the coating, now we'll go to the drying zone. You are seeing the oven. We have 3 meters of oven. So in each zone, we can control the temperature and we can control the airflow. Okay, this step is a very important step. Some people, they don't pay attention to this process, but it's really important because here we are fixing the microstructure of the electrode. If the temperature we are using for drying is too high, for example, we will provoke the migration of the binder towards the surface. If the temperature is too low, it will occur the opposite, that the binder will migrate towards the current collector. Okay, so very, very important to fix the temperature profiles in the oven. Okay, so let me talk a little bit about the process parameters. With this coater, we have the possibility to coat between 0.5 and 5 meters per minute. But our usual coating speed is 1 meter per minute because we are limited to the length of the oven. The maximum coating width that we can do is 275 millimeters because the width of the rolls are 300 millimeters. Sorry. So about the ovens, we can increase the temperature from 50 degrees up to 180 degrees. This is in the case that we are using NMP as an organic solvent. For sure, to be working with NMP solvent, it is necessary and mandatory to have a solvent recovery system that we have in our pilot plant. Coating quality. It is very important to have thickness accuracy. We need an homogeneity, not just in the coating direction, but we need to get this homogeneity across the direction of the coating. As you have seen, we just coated one side of the electrode. To do the second side, we take the roll and put it back at the beginning of the machine, and we do the coating on the second side. Okay, so now in the images, we are seeing the calendar. So during the calendering, the copper or the aluminum foil coated on both sides is compressed using a pair of rolls. So with calendering, we are looking for two different objectives, okay? The market is demanding very high energy cells. So that means that we need to have as much as energy as we can in the minimum volume as possible. So that means that we have to reduce the thickness of the electrodes. From the other side, with the calendering, we will homogenize the surface of the electrode. Okay, and this will prevent some possible short circuit during the working of the cells. So now in the images, you are seeing a lot of rolls, a lot of devices, but all of them, they are just guiding systems. We have to make sure that the electrode goes in the good direction in the calendar. The important part is what you see now in the image. These are these two big rolls. So the parameters we can control in in the rolls are the gap and the pressure. We have the possibility to warm up the rolls if it is necessary. It will depend on the densification that we are targeting, and it will depend on the chemistry. So in general, during the calendering process, we will reduce the porosity from 50% that we have after drying to 20–40%. It will depend a little bit on the desired electrode configuration. And just to finalize some process parameters, to get an idea, we can increase the pressure up to 20 megapascals. The calendering speed is between 0.5 up to 5 meters per minute. And one very important thing, the cleanness of the rollers. It is crucial to keep them clean, because if there is any dust, any particle or whatever, and we don't remove it, it will mark all the electrode. So very important at this point. And just to finalize, one thing is to consider the spring back of the electrodes, because sometimes after the calendering, we have this effect. So we have to consider it if we are targeting one electrode. Yeah, and it's all what I wanted to tell you about this block. So I think my colleague has gathered all the questions.
Yeah.
So maybe we can just start answering the questions.
Okay, so for the first question we have is that which mixing times do we use on average for the different slurries? So as Idoia mentioned in the introduction, for the laboratory work is very important for having these timings in the different addition of the materials to the slurries. So as you are talking about which is the average time, we will say that some of the slurries are done during the day. So maybe it takes 5 or 6 hours of mixing, and then we are doing the coating. But some of them we need more time, and we are adding some materials the day before. So, and we have some mixture time of the overnight. So depending on the formulations that we already set on the lab.
Yeah, actually, as Aitor is mentioning, the mixing time, it will depend a lot on the composition of the electrode. If we have nanoparticles or carbon nanotubes and particles that are very, very small, it's very difficult to make a good dispersion of them. So it will take time first to get the dispersion of these nanoparticles or nanotubes, and after we need to incorporate this dispersion to the slurry. So as Aitor said, I will say an average of 4 hours for the preparation of one slurry in the pilot plant. Yeah, Iker now actually is showing the mixer. Yeah.
Yeah. Okay. So maybe we can move to the next question. There is a question regarding how meters per minute we can produce of electrodes.
Yeah.
So,
as I mentioned before, our coater has a maximum speed, coating speed of 5 meters per minute. Okay, we can change from 0.5 meters per minute up to 5 meters per minute. But our limitation is in the ovens. We have just 3 meters of oven. So in these 3 meters, so that means if we are doing the coating or using a speed of 1 meter per minute, so that means that in 3 minutes, the electrode has to be dry, okay? So when we are producing thick electrodes, it's not possible to use 1 meter per minute, because there is no time to dry the electrodes. Because as I mentioned in my speech before, we cannot increase as much as we want the temperature, because this increase in temperature will provoke the migration of the binder. So we need to control, there is a balance between controlling the structure of the electrode and making sure that we are removing the water of the NMP or whatever is the solvent in the electrode.
Yeah, and regarding these questions, there are also, which is the drying temperature that we are usually use in the ovens.
Yeah.
So as Idoia mentioned, for example, with the graphite and the loadings that we are targeting, what we have the experience that using a ramp, for example, in the first oven and in the third oven, having a lower temperature at the beginning, just to start with a more easily drying and in order to not damage the electrode. And for the last step in the third meter of the oven is where we are doing with the higher temperature.
Yeah, and what I thought explain is working for both.
Yeah.
For water-based electrodes and for NMP or for organic solvents. So with water will be around 60, 80 degrees, something like that. And for NMP, we have to increase up to 130, 150 degrees.
Yeah. We have to optimize depending on the loading, which are the electrodes that we are producing, this rate of the drying during the coating machine.
Yeah, just to get an idea, for a standard electrode of 3 million per hour per square centimeter, something like that. This is quite standard for us. The coating speed will be around 1 meter per minute, and the temperature will be, the drying temperature will be around 60 and 80 degrees. Yeah.
Okay. So also there is another question regarding this drying step, and is about the airflow that they are applying, and if we have differences between the coating thickness in this airflow.
Yeah, here it's a combination between both things. It's we have to control not just the air that is coming in the oven. You know, Iker is showing. We have also to control the air that is going out, the exhaust. Okay, so for each electrode, you need to combine the temperature that we mentioned, the coming airflow. Iker is showing there is 300, 400 meter cubic per hour, and the exhaust flow. So it's a combination of these three parameters.
Okay.
Thank you.
So once we talk about these parameters, there are another questions regarding the calendaring.
Okay.
For example, there is a question regarding how we are doing the calendaring with heat here.
Yeah, actually, to be honest, we try to avoid the heating of the rolls, because it's from one side it's costly to heat the rolls. It's costly in terms of the energy consumption. But what the problem is to cool down the rolls, because it takes a long time to cool down. So we try to avoid that temperature. We use it in a very weird cases where the loading is very high and we need to reach very, very thin electrodes when the densification we are targeting is very, very high. But we try, as I mentioned before, we try to avoid this warming up of the rolls.
Yeah, and also there is it's true that we are trying to avoid it, but sometimes depending on the binder that we are working with, it requires to make this heating in order to activate this binder. So it depends on everything is depending on the formulation.
Yeah, actually sometimes there are some PVDF that they will require, you know, some to go above some TG, you know, to melt and to make this binder effect. So if we are working with this special PVDF, for example, so for sure then we are forced to do that. But with a standard formulation, I would say that
Yeah.
it's not necessary to warm up or to heat up the rolls.
Yeah, and another question regarding this calendaring process is that it depends on the cathode chemistry. And yes, of course, we need to optimize this because the density that you are targeting for NMC is different than for LFP. So, and of course, we are always trying to calendar the electrodes as much as possible, but they have to work. So in order to take the target of the density that we want, for example, with the NMC, yeah, we need to adjust the pressure, and it's different than LFP.
Yeah. There are some approximate values that we are using.
Yeah, for example, 3.2 grams per cubic centimeter. Of course, is a value that you cannot achieve with the LFP. So yeah, it depends on this. We are doing the experiments and we are seeing how we can achieve this value in density, and it's just experimentally in the calendaring.
Yeah, because as we will see later, you know, the electrolyte has to fill all the pores. So we need to keep a balance between the microstructures that we have obtained in the drying step and how much we calendar, because we are reducing the volume of the pores in the electrode. So it's important to keep in mind all these aspects.
Okay, so also there are another questions regarding the which is if we have in the planetary mixer more effective compared to high shear disperser with the nanoparticles or carbon nanotubes.
Yeah, it depends. You know, it depends on the material. The planetary mixer, based on our experience, I have to say that it's a very, very good mixer. And as I mentioned, it is very important to define the mixing procedure, okay? So if you are working with nanoparticles, you have two options. You can use a high shear rate device, you know, like ultra turras, for example. But you have to be aware that using ultra turras, you are introducing a lot of energy in the slurry. So you have to be aware that you have the possibility of breaking the particles. If, for example, you are working with a coated LFP, for example, you cannot use high shear devices, because during the preparation of the slurry, you will break the protective layer of the particle. With the high shear devices also, you have to be very careful when you apply this high shear. It has to be always before you add the binder, because otherwise you will break the chains of the binder. Okay, but sometimes it is mandatory to do that. When you have the planetary mixer, you know, considering this movement that you are seeing at the moment in your screen, what is important is to do what is called the kneading process at the beginning. So that means that at the beginning, you know, we'll have a slurry that will have a very, very high viscosity. Okay, so we'll have a lot of solid and not much liquid. So it will be like, you know, like you are kneading a bread, something like that. So this step is the most important one to control if you have to disperse materials that are complicated, like carbon nanotubes and so on. So I will say both techniques are okay, but it will depend a lot on the material you are using and on the electrode that you are targeting. So I think the good thing is the combination of both. Yeah.
Yeah. So also we are changing again to the calendaring. As we mentioned that the cathode calendaring of this NMC and LFP, there's a question regarding of that if it's true that the cathode that is more calendar is better. It depends on the requirements of the electrode that you want. It's true that for energy density, the highest is the loading and the lowest is the thickness. If it works in the battery, you will have the best conditions for this high energy. But you have to take into account, depending if you are thinking about the power applications, maybe these parameters should be changed. So this density values that, for example, we said about the NMC, that is 3.2, it depends on the application of the final battery. So we cannot say what is better. It's depend on the requirements that you want to target.
Yeah, this is what we were discussing before. You need to keep at least a minimum porosity, because the electrolyte has to wet the electrode. So there is a minimum value that you need to keep. And also, as I already mentioned, depending on the application, if you are targeting power applications, for example, then sure, I mean, you need to reduce as much as possible the thickness of the electrode, because the higher is the thickness, the higher it will be the resistance that you are introducing in the cell. But when you are designing one electrode, you have to consider all the process. I mean, coming back to the example of the high power electrodes, when you are thinking about high power electrodes, you know that you need to add a high percentage of conductive material in the slurry preparation. Okay, so when you design the electrode, you know that there will be a lot of carbon in the preparation. You will have to prepare it in a specific way. The thickness in the coating is not possible. It won't be possible to be too high. And after in the calendering, you will have to compress it as much as possible. And not just that, I mean, when you are designing the power application, you have to select the chemistry. You know that with LFP, the power capabilities that you will obtain in the cell, it will be higher, it will be better than with NMC. The same for the anode. I mean, you have to design or you have to decide which graphite you will use for this high application. There are graphites that are specific for energy, and some other graphite, they are good for power. So with this explanation, what I mean is that when you are thinking about designing one cell, you have to consider a lot of parameters. Okay, it's not that, okay, I will change the drying of the oven, or the drying temperature of the oven, or I will change the densification of the calendar. No, I mean, you have to consider the global picture for that.
Yes, according to Idoia, another question is, what is the loading that you are targeting? For us, it's depending on, as well in the application. It's true that if you are looking for a cell with high energy density, you are not going to use the electrodes that you are going to use for power applications. So in this period, we have to select which is the best loading and the best density that you need for your requirements. So that's why, first of all, we have to design how we want to have the electrodes, define it before. Irache already explained it in the session before. And when we are seeing which are these performance in the full cell, for example, in coin cell, and then we are seeing, okay, with these materials we can achieve these values, and that's why we want to upscale to the pilot plant. So
yeah,
we continue with the questions.
Maybe a couple of questions, because I think this is the most important part.
Yeah. Okay. So we are following with the calendaring system. There is a question regarding how we are doing, how we know that they are calendar after the calendaring, how is this difference. So what we are doing is measuring the thickness before the calendaring step, just to know which is approximately the porosity of the electrode before this calendaring. And then we are measuring the thickness after this procedure. So in that way, we can see how we compress the electrode and how is the evolution of this porosity after this treatment. And of course, the targets are Iker is showing now the values of, for example, they apply some pressure between the rolls. Yeah, and with these values that they are making this pressure between the rolls in order to reduce this thickness, and that's the parameter that they are playing for this densification. So I don't know if yeah.
Okay, so thank you very much, Iker. Now we have finalized with this block, so maybe we can jump to the second one. Okay, so the battery manufacturing plant is divided in Fidetec, is divided in two different labs. In the first lab is where we produce the electrode, and it's what we have explained in the first block. So now we have just entered in the electrode, in the cell fabrication lab. You have seen that my colleague, she has opened the window, okay? In a normal working day, for sure, we keep these windows closed because of safety reason, but today, due to get a better image, we have opened the door. We leave the doors open. So first, I will explain in this block, I will explain the die cutting is the machine that you are seeing now. After that, I will explain the stacking machine. I will explain the welding process, and we will see how we introduce the stack into the pouch foil. Okay, so the calendar rolls coming from the previous lab are fed to the station by a manual transport process. Now you are just seeing the die. We have two different dies, one for the anode and one for the cathode. Actually, now you are seeing the cathodic die. Yeah, you see it there, the cathodic die. The dimensions of each die, the dimension of the anode is different from the cathode. Actually, the dimensions of the anode are a little bit higher because we want to avoid the lithium plating during the working of the cell. With the dies we have, the final cell dimensions will be 14 centimeters times 23 centimeters. Later on, we'll see the cell. In this process, it is important, to remove or to extract away all the dust that we are generating during the cutting. Okay? Because these small particles, after, they might provoke a problem in the working of the cell. And following with this topic, I would like to mention that it's very, very important to keep all the machine clean. So it's not a good idea, to take the roll of cathode, to cut the cathode, and right after that, put the roll of the anode and do the cutting of the anode. No, I mean, the way of working here in Fidetec is you have to organize well the work. So if one day you are going to cut the cathode, fine, you cut the cathode. And after that, it's very important, to clean the machine, to clean it very well. Once you are sure that you have cleaned everything well, is when you fit the roll of the anode and you do the cutting of the anode. Okay, so you are seeing now that the sheets are positioned using vacuum gripper. Some process parameters for this machine, we are able to cut like 20 electrodes per minute. The tolerance requirements that we have are 100 microns with a length tolerance for the sheets. Here you see the inlay quality control we have. We take a picture of the sheet, and we have to control that the dimensions of the electrode are okay. We check that the position of the tab is the correct one, and we check that the distance from the tab and the edge is the correct one. If everything is okay, the arm you are seeing is positioning the sheet in front of the machine. If the machine detects something wrong in the dimension, in the tab or whatever, it will refuse the electrode, and it will put it in the back of the machine. Okay, so you are seeing that all the electrodes are collected in this special box, I will say, and this box will be transferred directly to the following machine, to the stacking machine. And one last thing to comment that is very important here in this machine, to keep a very good quality on the cutting edge. Okay, really important for this machine. Now you are just seeing an image of working of the machine, of the full machine. Okay, so next machine is the stacking. So my colleague Inigo, now he is just selecting the number of electrodes that he wants to compose the cell, and the type of electrode he wants to be included in the cell. And he just push the button to start the process. So during the stacking process, the separated electrode sheets are stacked in a repeating cycle of anode, separator, cathode, separator, and so on. There are different stacking technologies in the market, but the one that we have in Cidetec is the stacking winding plus the lamination station that we'll see it in a minute. So in this machine, we fit the role of separator. We fit the box that the box of anodes, the one that you are seeing in the image, and we fit the box of the cathode. So in this case, the anode and the cathode sheets are inserted in the separator, and the separator is used as in the form of an endless tape, and it's cut off after the stacking process. So in this equipment, the exact positioning of the individual sheet is considered as the central quality criteria. Okay, it's really important, this point. So here you are seeing the same than in the previous machine, that the sheets are transported by vacuum grippers. Now you are seeing in your screens, you are seeing the lamination station. So with this station, what we do is we apply a very light pressure and temperature to laminate the electrodes to the separator. So to be able to do this, we have a special separator that has a very thin layer of PVDF on the surface. So now you are seeing all the electrodes laminated to the separator. you have seen that we have the quality control, and we are checking the position of each sheet in the separator, and we are checking the alignment of the cell. If everything is okay, the machine automatically will leave the stack on the shelf. If something is wrong, the machine will detect it and will refuse it, as we just saw now. Yeah, so I have now my So now my colleague will take the stack. I have to say that at the end of the process, we put a little tape to avoid the movement of the separator. Okay. So the stack is connected with the cell tabs using the ultrasonic welding process. We have two different tabs. We have the aluminum tab, the one that my colleague is handling now for the cathode, and we have a copper tab for the anode. The copper tab is covered with nickel. So during the welding process, we can control or we have to control two different parameters. We have to control the time, and we have to control the energy that we are applying. Okay. So the time and the energy, they have to be adjusted for the anode, for the cathode, and it will depend also on the number of electrodes that we have. In our stacking machine, we can stack up to 50 sheets of electrodes to get a cell capacity of 30-40 ampere hours, something like that. You are seeing that my colleague is positioning the tab in the middle of the flaps, and he's using a guiding system. This is important because we're gonna have. It's important to have an alignment between the stack and the tabs. So now he will weld the anode in two different points, as he did for the cathode. Now in the image, you are seeing, like a transparent film over there. So this is an adhesive tape that it will be used in the next process to seal the cell. This is actually a very critical point, because if there is a leak of electrolyte, in general, it comes from this point. So it's important to seal very, very well in this point the cell. Okay, so once the welding process is finished, next step is the introduction of the stack in the pouch foil. Yeah, so my colleague is positioning the stack in the pouch foil. This pouch foil has been deep drawn in an earlier process. The width of the deep drawn will depend on the stack. It will depend on the number of electrodes that we have our stack. The packaging material is aluminum with several layers, 2-3 layers of a polymer. The role of this foil, this aluminum foil, is to prevent the diffusion of the humidity inside the cell. So in this with this machine, we seal 3 sides of the pouch. the sealing, for a sealing process, we have to adjust the temperature and the pressure we are using. One side of the cell is not sealed in order to be able to fill the electrolyte. As you are seeing here, the size of the pouch foil is bigger than the size of the electrode. We do it because in the forming process we will generate some gas that they will be allocated in this pouch, in this excess of pouch. So we finish with this, so
part.
now we can move to the questions.
Yeah, we collect the questions that you did. First of all, the question was which are the dimensions of the anode and cathode, because you explained about 14 by 23 centimeters. But of course, we have two different dimensions just to have sure that we are putting in the stacking machine, in the stacking winding machine, the cathode in front of the anode, and the anode is 3 millimeters higher in the length and in the width than the cathode. So in that way, we can be sure that all the cathodes are in front of the anodes. And for this, we have different. Iker is showing the both electrodes. How it's very small this difference, but of course this small difference you can see in the also in the corners.
Yeah.
And in order to assess this, we have different cutting dies for anode and cathode. And another question was regarding these dimensions and how we are doing the cutting, about the maintenance of the machines. So, for example, for this electrode cutting machine, we have the maximum cuts that we have to do before this maintenance is 5,000. Yeah, Iker is showing how is the counting of this, how many cuts already did this cutting die, and there is this part of how many cutting dies that we did, but as well we have also that if we don't reach these 5,000 cutting dies, every year we have the maintenance of the machine. So depending on how many of these cutting dies we are doing, we have one maintenance per year or more. And with the stacking wind machine, because it's related to another question, we have to set up this stacking winding machine, because depending on the thickness of the electrodes that previously we have designed, we have to select which is the. Maybe we can connect with Iker and we can see which is the distance between electrodes. This distance on the positioning of the electrodes depends on the thickness, for example, of the electrodes and how many electrodes we have of cathode and anode. And here in the screen you can see he can set how many cathodes and anodes we have in order to have this stack. You can see here that we have a hole here of the cathode, and this is why we are doing this cutting. You can see in the video that when we are doing the cutting between the cells, there is a place that the separator has bigger part, and here is doing the first roll. Yeah, Iker is showing as well. Yeah, here you have one gap to have the cutting, and another one that is more or less the size of the electrode to have the first turn of the first wind of this stack. So we have to set this, and also for this machine we have the maintenance every year, because we have of course some help to having the setup of this machine, and in order to see which are the parameters that we have to change to get the stat that we want. And yeah, and here Iker is showing how is this winding of the stack.
Yeah.
Yeah, and how is the distance, because the last electrodes are more separated than the first ones because we have this small part of the separator that is just in the edge of both electrodes. Yeah. So we have to set this for every stack. Of course, once we have one set of cells with the same chemistry, with same design of electrodes, it's already set and we can continuously done. Yeah, and here are the edges that we are saying in the. Yeah. Yeah. Thank you, Iker. So also concerning this stacking wind machine, there is a question about what is the separator that we are using.
Actually, as I mentioned before, our stacking machine is limited to laminable separator. So as I mentioned, the separator is mandatory to have a very thin layer of, it can be a PVDF, in general it's a PVDF, or it's a very thin layer of an acrylate. Yeah, Iker is showing the roll of separator. Actually, the appearance of this roll of separator is exactly the same than the appearance of a normal separator. You can find these two different separators in the market, the standard one or the one in this case that is laminable. What is important is when you choose the laminable separator, the PVDF layer has to be very, very, very thin, because this PVDF layer has to allow the lamination of the electrodes, but it's important not to introduce an additional resistance to the cell, because we are introducing one more layer. It's a polymeric layer, but we cannot allow us to increase the resistance of the cell. So in short, you can find this separator in the market, but you have to choose the good one.
Okay. So another question that we are having is something related from the previous part. That is how we track the quality of the electrode along the whole roll. So we didn't explain before, but we are doing some validations along the meters of the roll. But as you saw in the video, we are doing the coating with a knife, and we are seeing which is the loading. But of course, we have to be sure that for all the meters we are having the loading that we are targeting, and the same with the calendaring. As Iker is showing, we have the quality control here about the cutting with the machine that they are, as Idoia explained, making pictures about all the electrodes. So, and we have some tolerances that are 100 nanometers. And if in the cut we are seeing that we have this 100 nanometers deviation, the machine automatically discards this electrode and is putting to the back part. Now it's taking all the electrodes, so you can see that the cut is very clean. Maybe Iker can take one electrode just to see that how are the edges of these electrodes. Yeah, he stopped the machine, and I think now he is going to take an electrode to see how is the. Yeah. Yeah. Yeah, we can go to the corners and the edges. We can see that they are cut it very clean. We are not seeing very. We cannot see that there is any particle that are going out from the electrodes, and it's very clean now. So.
Actually, when he's bending the electrode, you are seeing through the good quality of the electrode. So that means the addition of the electrode to the current collector is quite good, because you are not seeing any delamination.
Yeah, that is something that we optimize in the lab part, and of course when we are doing the coatings in the pilot plant, these electrodes are previously checked if the peel strength of these electrodes are good enough, because we have to be sure that when we are handling the electrodes, we are not having any detachment of the particles and so on. So that is controlled first of all during the coating, and with this peel strength after the coating. And up to now, we don't have more questions in this part, so maybe we can move to the next one.
Okay. Okay. So yeah, let's go then with the third part, where we'll explain the drawing of the electrodes, the electrolyte filling, and the forming. Okay, so the drawing, it is a very, very important step, because as you have seen, all the processes are done at ambient conditions. So the stacks are dried in the vacuum oven inside the dry room. The drying time is approximately between 12 hours and 24 hours. It will depend on the electrode. And during this drying process, we will remove all the residual moistures of the electrode. The drying conditions are optimized using the calf fisher. Okay, we have prepared now a stack that is dry. So next step is the filling of the electrolyte that is done with the machine that you are seeing in the image. So here we have to distinguish between the filling of the electrolyte and the wetting of the electrolyte. Okay. So first step is the filling of the electrolyte. Iker is just putting the cell. It will introduce it in the machine, and the electrolyte will be filled into the cell under the vacuum using a needle and a high precision pump. So when we have added the electrolyte, the next step is the wetting of the electrolyte. So how we do that? We applied what we call a massage to the cell. Okay, so we apply a pressure profile to the cell. So we generate some vacuum, we break the vacuum, we generate the vacuum, we break it, and we activate the capillary effect, and the electrodes will be wet little by little. This evacuation and partial filling is repeated several times, depending on the cell type. It will depend on the electrode, and it will depend also on the type of electrolyte. Okay, because sometimes some electrolytes are easier to be introduced in the pores of the cell. Finally, once we have finalized with this massage, the pouch foil will be sealed under vacuum. Quality features that we have to consider once we have finalized with this process. We have to make sure that there is no electrolyte residue in the sealing sim. Otherwise, it will give us problems later on. And we have to check the tightness of the sealing cell. Okay, so now we have the cell. So next step is to go out to the testing lab. So first thing is to check that all the assembly process went well, that there is no problem. So for that we have the jockey, and we measure the voltage and the resistance of the cell. Okay. To do the forming of the cell, we do it between the two plates that you are seeing there. Okay, so my colleague is just putting a temperature sensor, because it is interesting for us to control, or yes, to analyze the temperature evolution during the forming. So he positioned the stack in one of the plates. He will put foam just to make sure that the pressure or the force that we are applying is distributed in an homogeneous way along all the surface. Okay. So for formation, the cells are charged or discharged following a very defined current and voltage curve. So during the formation, the lithium ions are or they are diffused to the graphite on the anode side, and we are forming what is called the solid electrolyte interface. That this is an interface between the electrolyte and the electrode. During the formation of this solid electrolyte interface, some electrolyte will be degraded. It will be degraded and it will generate some gas. So the gas that is generated during the formation, it will be accumulated in the excess part of the pouch foil. So yeah, my colleague just finished applying the torque. And now, next step, it will be to take the cell to the climatic chamber. Yeah. So during the forming process, as I mentioned, we have to define the current, we have to define the voltage, and we have also to define the temperature. Depending on the conditions that we applied in the forming, we will define the mechanical structure and mechanical properties of the SEI. Now my colleague is just connecting the current cables. He will connect also the voltage sensing, and he will also connect the temperature sensor. So the forming process, it will depend on the chemistry, on the cell we are working with, but it will take approximately 2-3 days. Yeah, now he just closed the climatic chamber, and we will just do the forming. Yeah, so once the forming has finalized, the appearance of the cell is the one that Iker is showing. Is very floppy because of the gas that we have generated in the cell. So what we have to do now is to remove this gas. So for that, we have this machine where we will make some vacuum, and we have a needle that will penetrate, and we will be able to remove all the gas. Now you are seeing in the screen how it's doing the vacuum to remove all the gas. Yeah, you are seeing in the screen. It's not seeing. You cannot see it very well actually, but you have in the screen the vacuum parameters that we reach during this process. So it's very important to remove all the gas. Once the gas is removed, the cell is sealed under the vacuum, and now the cell is ready. I mean, the only thing is that is left is just to cut the excess of the pouch foil, and the cell is ready for testing. Yeah. So here it is the cell.
Yeah. So okay. Yeah, there are some questions here. Okay, so first of all, the first question was how we transfer this stack from the vacuum oven to the electrolyte system. maybe it was not appreciated, but the Iker at the beginning was in the dry room. So the stack, once is dried in the vacuum oven, is in the dry room conditions. So of course there is some water in the air, but it's very low. In this dry room, we are working with a dew point of -40 degrees, and we are transferring directly from the oven to the electrolyte filling machine. They are doing the filling of electrolyte and making the massage and seal it under vacuum. So once when we have done all the experiments with these cells, we have never faced problems, and we have to say that all the cells that we are doing with lower capacities, because of course with this pouch cell size, we are using for example 30 ampere hour cells, but for lower capacity cells, we are working in this dry room, and we are doing all the steps there. We didn't face any problem in the electrochemistry.
Yeah, actually, this drying step inside the dry room is crucial for us because, as you have seen, all the processes are done in ambient conditions. So we really have to make sure that we dry very, very well the stack. So for that, we have the calf fisher.
We know the maximum water quantity that is allowed in the electrode. So we will be changing the temperature and the vacuum of the oven until we reach this maximum of water that are allowed in the electrode.
Okay. Okay, so we can move to another question. Concerning the electrolyte filling, they are asking how is the filling of the electrode, which is the amount of electrolyte that we are used to work with these pouch cells. Of course, with the as Idoia mentioned, it depends on the chemistry, because of course we have to fill at least the free volume that we have in the cell, because the electrode has the porosity that we have defined before. Also, the separator has its own porosity. So first of all, we make a calculation about this how is this volume, and we have to add extra volume that we have already optimized for this kind of cell, and that's what we are ensuring that the electrodes are soaked and the electrochemical behavior is not going to be affected by this. Of course, it's not for us. It's not good to have a very low amount of electrolyte because there are some active material that is not working. But it's also true that having a lot of electrolyte is not well as well, because the cell is not in a good condition. So we have to do this optimization before with the calculations that we do with the porosities. And for every system, because the layers that we have, the porosity of its electrodes, we have to calculate this for every type of cell. Of course, once we have this cell that is for all the cells, for example, if we have to make this 50 cells of one batch of this kind of chemistries and design of electrodes, for all of them are going to be the same electrolyte amount. So also there are questions regarding the drying temperature. I guess that they are saying about the drying temperature of the stack. We have to see that the main problematic part of this drying is the separator, because once you are doing the drying, the separator is the material that is melting before than the rest. And you have to be sure that you are not changing the chemistry and the parameters of the separator. So a typical temperature should be 60, 70 degrees C for the separator that we already used. However, depending on the polymer of the separator, of course, if it's more stable, maybe you can go to higher temperatures, but we have to set this with the separator type that you have in the cell. Also, there are questions regarding the metallic plates during the formation. And also the question about this is if it is used to guide the gases to the additional part of the pouch cells, and the answer is that yes, it's just to do this, and in order to avoid that we have the gases between the electrodes. We are moving these gases to this additional part, and we are making sure that the gases are not having an influence in the electrochemical behavior. So another questions are regarding the current density of this formation cycle. Usually, it's true that there are differences between these formats of the cells, but we have already optimized this part of which densities we are going to use in the formation and also in the test previously in the coin cell. After that, sometimes in the pouch cells, but with a lower size than these ones, and then we are making this in the higher in these big pouch cells. So the current density, the standard formation cycle usually is at lower rates, for example at C/20. So this formation of the cell, it takes around 2 days with this rate. But of course, depending on the formation cycle that you want, because sometimes you want to have a longer cycle or having more than one cycle. This is up to the conditions that you agreed in the project that you have, or you want to select, because you want to be sure that the forming is completed. So it depends on that, but yeah, the standard one is the C/20. Okay, so how do you degas and get the cell out under vacuum? Do you gas and seal one more time? Maybe here we can go to Iker again. What we are doing is, once we are doing the forming, you can see that the cell is you have some place that, and of course you are not seeing that the stack is marked, and this is because the cell is not under vacuum. So what we are doing in this machine that Iker is showing, we insert the cell with the tabs, and with something that covers the tabs in order to avoid any short circuit of the cell. And you are setting that that you are doing the vacuum in order to remove the gases, and after removing all the air, you are doing the sealing. So the cell is sealed under vacuum, and you can be sure that you don't have any gas that is coming from the air atmosphere.
Yeah, maybe I don't know if we can go back and maybe, because we didn't see very well the parameters.
Okay.
There was some reflect on the screen here. I don't know if we can somehow. No, there is a. No, there is some reflect of the like we cannot see it. It doesn't matter. It was just to see the parameters of the vacuum, but yeah.
No problem, no problem. Yeah.
Now much better. Yeah. Now much better here. Yeah. Thank you.
Okay, so there's another question. This is regarding the electrochemical test. That is, let's say, something that we are going to see later. But just for the forming, we can say that Of course, for the forming, we are doing this test for all the cells. And of course, every cell has its own measurement of which is the voltage before and after the forming, also in terms of voltage and in terms of internal resistance. Usually, when you are doing a set of cells, the difference between the voltages and the internal resistance is very low. So it can give us a clue if we have any problem in one specific cell, if we are seeing that the values of voltage or the internal resistance that we have is something that is coming from a problem inside the cell. So in order to do that, as is saying in some questions, the impedance spectroscopy can play a very important role, because depending on if you are doing the measurement with the multimeter of which is the resistance of the cell, you have the value, but you don't know which are the reasons behind of this high internal resistance. So with the impedance spectroscopy, we are able to see if there is any part or any interface that is enhancing this growing of the internal resistance. So, okay, we have now a lot of questions. How long does it take for the electrolyte to wet all the parts of the cell? Of course, for this, we are working with standard electrolytes and with the porosities that we know. So more or less this we have quite optimized. We have to say that with several hours, we are sure that the electrodes are soaked. And also there are, depending on the chemistry, we are doing some formings that are with temperature, and or we are doing different than one cycle at C/20. So that is specific of each cell. But for example, working at 40 degrees in a forming for the formation in the cell, you are ensuring that with the time that the electrodes are soaked, but also having this forming in temperature, you make it easy to the electrolyte penetrate, because with this temperature, the density of the electrolyte can vary and can facilitate this electrolyte soaking of the electrode. So, okay, there's maybe, I don't know how we are going about time, but
yeah.
Okay, so okay. Okay, so there's a question regarding when and how the pouch cell is finally sealed after the electrolyte insertion. Okay, so if you remember during the video, first of all, we take the stack and we put inside the electrolyte filling machine. And from that part, we have the cell already sealed with this excess of pouch bag. Then, as my colleagues saw in the characterization part, they put into the plates with this extra that is taken out from these plates, doing the formation cycle and the generation of gases. Once we have this, we are going to the machine that Iker saw before. I don't know if we can connect with Iker now. Yeah, no, it's to the other machine. Iker? Yeah. Okay, he's taking a cell with this excess and put it again here. We insert in the degassing machine seal as we have in the in the characterization. We put inside
we have the two bars up there to control the temperature and the pressure to seal the aluminum bag.
Yeah, and this temperature is depends on this aluminum bag. In this case, our aluminum is having these layers that Idoia mentioned of polymer. In this case, for us, depending on this, we can set the temperature, as Iker maybe can show. And for the sealing bars is the temperatures,
105.
Yeah, yeah. And one thing that is very important in this part is that the cell has to be set in a very correct way, because there is these needles that they are making the holes is done in this extra part. Yeah, you can see here. And here is the final seal of the cell in the sealing bars that Iker showed before. So we have two last sealings. First one is for the formation with the extra part, and the final one with this extra part. And with this extra part, of course, is the cell as Iker is showing you. And then we are cutting this extra part that is already with without the extra part in the machine that we have. Is in the other side. There is a cutting machine that is to have to do this cutting. We put there, and and they are cutting the bag, and you have the final cell. Yes. Yeah. Yeah. Okay. Okay. Thank you very much, Iker.
Yeah.
Okay. I don't know. We have question for one more.
One more if you want.
Okay.
One more, and we'll jump to the last block.
Okay. There is a what is the maximum temperature we are sensing with the thermocouple during formation? When we are checking this temperature, we didn't, as we are doing sometimes the temperature, the forming temperature, we can see as we are doing also the formation with low rates. So the temperature of the cell is not increasing a lot. So maybe 1-2 degrees is the temperature that we are seeing that is varying this cell during the forming, but it's not a very big impact that we can see. And of course, most of the cells, we are not seeing a high difference between the temperature. That is something that is happening in the cell. That is something that we are seeing more in, for example, in power test, that you are using very high currents and you are stressing a lot the electrodes, and there you can see more this difference in the voltage. But of course, we have this thermocouple in order to be sure that if we have any increase in the temperature, we have to stop the test and then take the cell, because there is a problem there.
Okay. So now it's almost 4. So maybe now we can jump to the last block, that it will be the characterization of the cells. Okay, so now let's jump to the testing lab. So before we start with the electrochemical characterization of the cell, as we did before the forming, to make sure that the stacking process went well, we do the same here. We just measure the voltage and the resistance of the cell, just to make sure that all the filling the filling of the electrolyte and degassing and so on, it went well. Okay, so the characterization of the cell, it is done between the plate, and the characterization that we will apply to the batteries, to the cells, it will depend on the application. If, for example, we are thinking, or we are testing a high energy application cells, it is very important to study the cyclability of the cells. So this test will give us a clue about the lifetime of the battery. So in this topic, the reference value as end of life of the battery is when it arrives a cycle where only the 80% of the initial capacity is obtained. when we are testing this type of cells, it is important to understand if different temperature, storage time, and so on can enhance the degradation of the battery and consequently reduce the lifetime. If we are thinking about power applications, rate capability tests are performed for analyzing the performance of the battery when they are submitted to fast charge or discharge. So power test can carry out in order to evaluate the response of the battery by high current peak due to a specific high demand of energy of the battery in a small period of time. Now you are seeing that my colleague is connecting the cell in the climatic chamber. For testing cells, actually, Tech opened like 2 weeks ago a new battery testing facility, mobile. In total, we have more than 750 channels of conventional small pouch cells. We have at the moment more than 400 channels for big cell with a capacity of 100 ampere hours. We have 65 channels for modules, 4 channels for battery packs. And very important too is the abuse test. So we have a machinery to run some overcharge, over discharge, signal penetration, and so on. So yeah, with this was a short video. We have finalized the explanation about the characterization. So
Okay.
now we can jump to the questions.
Okay, maybe we can start with some of them that were left from the previous batch because.
Okay, good.
So if we are, one question is if we are doing any test to ensure that all the corners of the electrode stacks are soaked properly. Of course, one thing that we use to do is to when we are working with the electrolytes and so on, we have to be sure that everything is soaked, as you mentioned, because if not, we don't have the this part of the electrode that's not working. So first of all, some fresh cells are open in order to be sure that all the part of the stack is wet. If not, we have a problems there. And also, when we are doing this electrolyte, because there are many questions about this electrolyte, making sure that all the electrolyte is in the electrodes, we can see that when we open the cell, how is the distribution of this volume of the electrolyte, and also to be sure that all the corners of the electrodes and the separator is wet. So this we are opening the cells and checking that everything is wet. And also another question regarding the previous part is if we carry out the analysis of the gas generation generated after the formation. We are not used to do it, but we.
Yeah, actually, with the new facility that I just opened, we'll have this device. We have a calorimeter, and it will be will couple a gas analyzer. So we will be able to analyze this gas or any other gas that might provoke or might be provoked by the degradation of the cell.
Yeah. Up to now, we only have the machine that Iker showed, and there is doing the vacuum and everything is extracted. So we are not facing this gas once we are opening this box. But yeah, everything is extracted and we are not analyzing this. Okay, there's another question, and now it's about the characterization. Okay. Why the characterization is done with 2 plates? Is the cell performing better when it's between the plates compared to the freestanding cell? Of course, we are doing this characterization between plates, but not for all the cells. Sometimes we are doing for example, there are some cyclings that we are performing without plates, and they are working well as well. But it depends on if you want to see if there are electrodes that can suffer with high volume expansion and so on, and maybe you can be sure that you have a very good contact inside the cell.
Yeah. Sometimes also we are simulating the pressure that the cells are facing in the module. You know, some clients, they tell us, okay, so my module has this design, and in my module the cells will be submitted to this pressure. So sometimes we try just to emulate the ambient that the cell will see in the module. On top of that, today we just talk about lithium-ion batteries. As I mentioned, we can use the plates or not, but for example, if we are testing solid electrolyte batteries, the using of plates is mandatory. We will need to apply some pressure to be able to get the best performance of the cells when we are working with a solid electrolyte.
Yeah. And as well, there is another question regarding if we are able to perform the post-mortem analysis. Yes, as I mentioned, with that one check that we are doing is if these cells are soaked. As well, we can do this post-mortem analysis because, as it is mentioned in the question, regarding the cycling and power test, we have to check the degradation of these electrodes. Of course, before opening the cell, we are doing some checkups, cycles, in order to see how is the evolution of this internal resistance of the cell by DC. But as well, we are measuring the AC impedance spectroscopy when we want to see, as I mentioned before, if there is any specific part of the cell that is failing.
Yeah.
Because and sometimes it's because one cell have a strange behavior, and that's why we have to combine the post-mortem and also the impedance spectroscopy to maybe have a conclusion on which is the failure in the cell and which type of if sometimes it's that is you are running out of electrolyte or you are seeing that you are increasing one interface in between the electrodes. So depending on that and with the visual inspection in the post-mortem analysis, maybe you can take a conclusion.
Yeah, actually, post-mortem analysis is very important here in CDTech. And for this post-mortem analysis, we combine the physicochemical characterization with the electrochemical characterization. For physicochemical characterization, we will open the cell and we will take some pictures. We'll analyze if the morphology has changed. We will take some X-ray measurements to see if the crystallinity of the material has changed and so on. So we will combine these electrochemical or physicochemical measurements with some electrochemical measurements. And as I said, the combination of these two of the different techniques will give us a clue of the failure mechanism of the cell. And this is important for us because in CDTech we are designing cells. So if we understand why a cell has failed, it will help us to improve the next design. If we have lithium plating, we know that in the next cell design we will have to increase the anode correctors, just to give you an example. Or if we run out of electrolyte, we know that we need to add more electrolyte. So post-mortem analysis is a very, very important topic if you want to move forward and advance in the cell designing.
Yeah. So also there is a question regarding the performance of the cells. If we are doing for each cell every test or we are taking some random pickup of one batch. Of course, once we are doing the formation and checkup cycle that all the cells are behaving the same, we are dividing the cells because, for example, if we are doing the power test, of course, we are making a degradation in the electrodes that can impact in the cyclability. So just to characterize well the cells, and let's say we want to have the fresh cell, for example, for the cyclability, because if not, maybe you are thinking that you have a worse cyclability that in reality you have. And the same for the power test. If you are checking which is the power capability of the cell, but you are taking one cell that was on cycling during 500 cycles, of course, the power capability will be worse than at the beginning. So yes, but of course, there are some tests that can be done in sequence and without any impact in the cell, because for example, if you are doing the cycling at one example is 1C rate, and you want to do a checkup cycle at C/3, this checkup cycle is not enhancing as the degradation as, for example, a power test. So you have to select how to divide these cells in order to take the full characterization without having any impact of a very stressful test in another test. So there are questions regarding the reference electrode.
Okay, let's move to that because we still have time.
Yeah. So if we are used to introduce a reference electrode in cells.
Yeah, actually, we are working on the development of our own reference electrode, and we introduce a sensor for temperature inside and a sensor for pressure. But these two types of sensor, they are commercially available. So the only thing we do is we just have to choose the positioning of these sensors inside the cell. But you know, the market is demanding the sensorization of the cell. As I mentioned, temperature and pressure. These are sensors that are available in the market. But there is a lot of work to do in the reference electrode, and this is something that we are working on.
Okay. So there is a question regarding the cycling machinery. We have
the what?
Yeah, the cycling machinery that we have. We cannot connect now with the cycling machines, but we can tell you that for coin cell testing we have more than 700 channels.
Yeah, we have a lot of, actually this is, I mean, behind us you can see all the channels we have for testing coin cells and small pouch cells. And for testing of big cells, we cannot connect because there was no connection, so we don't have a camera there. But if you go to our web page, you will be able to see the capabilities we have. And actually, if you click in the link to mobile, you will see there all the equipment we have for battery testing.
Yeah, and there are no more questions. There is one last one. It's about the stack the cells into modules. It's more about the.
Yeah, actually, in Fidetech, we are covering the full value chain and growing from materials up to the battery pack level. Today, we have shown just the battery production, but we have an engineering team dedicated to the module design and to the battery pack design. They do the mechanical design, the electrical design, the electronical design. They develop the algorithms to be implemented in the BMS and so on, and we are able to build the modules and the battery packs. We build the prototypes, and these prototypes are transferred to the clients.
Okay, so there are no more questions in this part.
Okay, so then I think it's all from our side. So thank you to all the attendees for being here. Thank you, Aitor. Thank you the people that was in the lab, and thank you very much to all the people that is behind the cameras. So yeah, now I leave the floor to, I don't know, Alexis or Silvia.
Alexis,
Yes.
maybe you want to.
Thank you so much. I think this was really great. That was fantastic and pretty unique. I think it's a really good opportunity for many students who actually never saw such a production line to see all the steps one after each other. And I think clearly this is something the field is recognizing the need to understand more and more and to work together between material science and manufacturing. And this is clearly we cannot do one without the other. So thanks a lot for this, and I think this was fantastic.
So I just thank you all again. Thank you to all speakers that attended today. Thank you to all students that attended. The registration of today's session will be on the Battery2030 website in the education session, maybe in 1 week, something like this, just to recap and to get everything well done. So I think that we got our first webinar on cell production. Next one will be most probably at the end of this year. So keep in touch, attend our Battery2030 website and all Battery2030 initiatives. And so have a good day. Thank you again, everyone. Thank you.
Thank you.
Thanks, everyone.
See you soon. Thank you.
Thank
Bye-bye.
you. Bye-bye.
Bye.